Assalamualaikum students. Today we'll study about the concept of soft, hard, acids and bases. Concept is shortly known as the SHAB concept. So before going into this concept about what's SHAB concept, let's define the terms of an acid and a base. So in SHAB concept, an acid is actually a Lewis acid and a base is actually a Lewis base. So acid is an electron pair acceptor, while base is an electron pair donor. So you've heard about this Lewis concept of acid and bases during formation of coordinate covalent bond, where an atom, which is positively charged, which is normally a metallic cation, is forming a coordinate covalent bond with some heteroatom having a lone pair, such as nitrogen. And we know that since nitrogen is donating a pair of electrons to the metal, therefore we say that nitrogen is donor while the metal ion is an acceptor. So here the metal ion is normally known as the acid because it's accepting electron pair, while the nitrogen is acting as a base because it's donating to electron pairs, right? So this concept of SHAB was actually proposed by scientists named as Ralph Pearson, who introduced this concept of SHAB, also known as the hard, soft, acid, and base. So it doesn't matter if you say hard, soft, acid, base or soft, hard, acid, base. It's just a matter of preference. So according to Pearson, when he introduced this concept, he says that hard acids prefer to coordinate with the hard bases, while soft acids prefer to coordinate with soft bases. Right? So this is a concept of like reacts with like or like binds with like. So he actually carried out this explanation. He generated this explanation of SHAB concepts in order to unify organic and inorganic reactions and in order to justify, to explain why some reactions are very rapid in taking place while other reactions are very slow. Then in 1983, after 20 years of his first definition, Ralph Pearson, along with another scientist, Robert Parr, he formulated a qualitative definition of SHAB concept and converted into a quantitative one by introducing the idea of polarizability. So the revised definition of the SHAB concept became that a less polarizable atom or ion is hard, while an atom or ion which can be easily polarized is soft. So let's now talk about the polarizability. Right? The capacity of a group of atoms in a molecule or capacity of group of atoms in an ion to polarize its electron is called polarizability. Right? For example, suppose that we have a atom in a molecule. Suppose this is the nucleus of that atom, and surrounding this nucleus are electrons. Right? These are the electrons here. So what happens that if this atom in this molecule is able to polarize its electrons, means it can shift its electrons to one side, a nucleus on one side, like this one. So the electronic density has moved away from the nucleus. So this end of this atom has become partially negative because it's rich in electrons, while this end is partially positive because this end has a positive charge because this end is predominantly surrounded by, is occupied by the nucleus, while the electron density has moved on the other side. This is known as polarizability. So if an atom is of larger size, for example, if an atom has a large size and other atom has small size, so you can just see by yourself that it is very difficult for the nucleus, for the atom of the small sized atom to polarize its electronic density because the nuclear pull on this electron will be very, very strong. As a result, it will be very difficult to polarize this atom in this manner. So that electronic density moves away from the nucleus. But if the atom is large, it means its electronic density is very much. It's larger. So as a result, the electrons that are in the valence shell are quite far away from the nucleus. So as a result, the pull of this nucleus on the valence shell electron is very poor. As a result, it's very easy to polarize such electrons in this atom as a molecule. So for example, here we have example of ammonia. where this nitrogen and this is hydrogen. Same is that since nitrogen is electronegative, it's pulling the electronic density of hydrogens towards itself, right? So this is nitrogen, which is pulling electron density from the hydrogen. So in this manner, it's not the atom which is actually being polarized, it is the molecule which is being polarized. So here in this case, since nitrogen is drawing electronic density towards itself, so it has a higher negative charge, while hydrogen, since they are donating the electronic density, so the hydrogens are feeling the deficiency of electrons. As a result, the hydrogens are positively charged. So here we have a polarized molecule where nitrogen section is having partial negative charge, while the hydrogens being deficient are occupying a positive charge here, right? So according to moving to the definitions of the SHAB concept, so we said that we have soft acids, we have soft bases, similarly we have hard acids, and we have hard bases. So we are having four terms here, and we have to define what do we mean by the soft and what do we mean by the term hard, right? So when we say the term hard in SHAP concept, hard mean that any species that has very small size, because of its small size, it cannot be polarized or it is very hard to polarize, right? And there are very strong electrostatic interactions between the positive and the negative charges, right? While in case of a softer acid or a softer base, such acids or bases have larger size. As a result of their large size, they are easily polarizable. Just we have seen in this case of this large size atom. And since they are easily polarizable, so they can develop easily strong covalent interactions by means of electron sharing. Right? So if an atom has a very small size, it prefers to donate or accept electrons. Just in case of ionic bond, you say that in case of an ionic bond between a sodium and a chlorine, say sodium has a small size and it becomes positively charged ion, which again much more smaller in size, while this chlorine has a negative charge because it gains the electron donated by the sodium atom. So in case if chlorine had a very large size, it would not have accepted an electron pair, because if chlorine had a large size, then accepting electron would have led to repulsion between the existing electrons and the incoming electrons, right? So that's why we have defined this term as hard and this term as soft. So you just have to remember that anything that is hard has a small size, right? And it will have a higher electronic density. While in case of a softer acid or base, its size will be large and the electron density will be uniformly distributed throughout the atom or the ion. So now we'll consider about the applications of SHAB concept. Why SHAB concept is important? The SHAB concept is important in explaining hydrogen bonding, because strong hydrogen bond is possible between oxygen and hydrogen, between in case of ammonia molecule, in case of water molecule, in case of hydrogen fluoride, because the donor atoms, which are oxygen, nitrogen, and fluorine, right? They are hard acids, while they are hard bases because they are having a lone pair, while hydrogen is a soft acid, right? So soft, why are saying that, sorry, hydrogen is a hard acid? Why we are saying hydrogen is hard acid? Because hydrogen has the smallest size, and further hydrogen is having a positive charge. So a large charge on a small size atom makes it very hard, while these are the first member of their series. So fluorine is first member of group number 7, it has 3 lone pairs. Oxygen is member of group number 6, it has 2 lone pairs, while nitrogen is member of group number 5 and has 1 lone pair. So all of these are the smallest atoms of their groups. So all of them are hard. So since according to the SHAP concept, the combination of hard and soft is very stronger. So in this case, the hydrogen bonding between a hard acid, which is hydrogen, while a soft and a hard base like oxygen, nitrogen, and fluorine leads to very strong interaction. If the atoms were of larger size, for example, if we have sulfur other than oxygen, because sulfur and oxygen are from the same groups, they both belong to group number 6. In such cases, the hydrogen bonding between hydrogen and sulfur would not have been much stronger because this is a soft hard combination. Right? The other example is the explanation of linkage of ambident nucleophile to the metal atom. So an ambident nucleophile is actually a nucleophile that has more than one donor site available. For example, in case of SCN, right? So we have two donor sites. One is cyanide site, which is a small sized group of atoms, while the sulfur is having two lone pairs. The sulfur has a large size, right? So here in this case, the cyanide is a hard donor or hard base, while sulfur is a softer base. So it depends on whether it's coordinating with a hard acid or soft uh, acid, it will make a difference. For example, if we have a platinum 2 positive, right? So platinum 2 positive, since it's having a 2 positive charge, means it's an acid. And we have chromium, and it has 3 positive charge, right? So chromium having 3 positive charge has a smaller size, while platinum having 2 positive charge is a softer acid. So if we are to combine, if we are to react cyanide ions, so cyanide will preferably coordinate with the chromium because cyanide is hard and chromium is also hard, while the sulfur, being a softer center, will prefer the platinum 2 positive as counterpart because soft combination and hard combination are more favorable than soft hard or hard soft concept combination, right? Another application of the SHAP concept is the explanation of site preference for organic reaction. For example, if we have the carboxylic acid halide, so we have represented carboxylic acid halide as RCOX, is basically this one, right? So this reacts with the cyanide preferentially, right, instead of sulfur. Why? Because this is a hard acid. Why it's hard acid? Because the halogen is withdrawing the electronic density from the carbon of the carbonyl. Also, the oxygen is withdrawing electronic density from the carbon of carbonyl. As a result, this carbon of the carbonyl is becoming very positively charged. So higher the charge, uh, harder will be the acid. So here, this electron pair acceptor, this Lewis acid, is because it's deficient. So anything that's deficient is an acid, right? So this carbon being deficient is an acid, and since it has a greater partial positive charge, it's a hard acid. So here we have SEN, and in SEN previously we have described that cyanide is a hard center, it's a hard base. So cyanide will prefer to attack because the combination of hard and hard will be more favored as compared to combination of this soft sulfur with this hard center, right? So here in this case the reaction will preferably carried out by attachment of sulfur, the nitrogen with the carbonyl, right? But in case if we have a simple methyl halide here, so the methyl halide is not as partially positive as with this carbonyl, so this is comparatively a softer center. Since methyl halide is a softer center, it is not that much charged, positively charged, as the carbonyl of the acid halide. Therefore, the sulfur will preferentially attack instead of cyanide, because now here the soft-soft combination will be more favored. Further, another application of the SHAB concept is to predict the outcome of some inorganic reactions. For example, if we have arsenic fluoride and we have phosphorus pentaiodide, the reaction is a double displacement reaction. So why this reaction occurs is a result of the basic concept that the arsenic is a soft acid and iodine is a soft base, right? While fluoride is hard and phosphorus is also hard. So fluorine will prefer phosphorus because both are hard, and arsenic will prefer iodine, both are soft. So that's why this product is very stable, and this product is also very stable because this product results from soft-soft combination, and this product results from a hard-hard combination, right? Another example is the reaction of magnesium sulfide with barium oxide. Right? The reaction occurs and results in formation of magnesium oxide and barium sulfide. Right? Why this happens? Because the barium has a larger size. Since size is larger, it means it's softer, while sulfur also is softer. So sulfur has lone pairs, it means its donor, means it is the base, while barium has two positive charge, means it's an acid. So the combination of soft acid and soft base result in formation of barium sulfide, which is a stable product, while combination of magnesium, which is a hard acid, with oxygen, which is a hard base, result in more stable combination, resulting in formation of magnesium oxide. Right. Another application of the SHAB concept is the precipitation reactions. So softer acids like silver, mercurous, mercuric, and water-like acid like ferrous, nickel, cuprous, zinc, lead can be precipitated as sulfides. Right? Why they can be precipitated as sulfides? Because the acids are soft and the sulfur is also soft. Right? So the result will be formation of stable product which will be quickly precipitated in the form of the desired precipitates which can be easily separated. Another application is the nucleophilic addition of alpha beta unsaturated carbonyl compounds. So these carbonyl compounds have two types of electrophilic centers. One electrophilic center is the carbon-carbon double bond, and the other is the carbon-oxygen double bond, right? So since here the carbon is partially positive, it has larger positive charge. So since larger size, it will be a hard center, while in this case, it will be a soft center, right? So since this is a soft electrophilic center, so soft nucleophiles will attack this position, while this is a hard center, this will be preferentially attacked by hard nucleophile. So let's apply the reaction, some examples to this concept. So here we have an alpha beta unsaturated system. We have this hard center. This is partially positive carbonyl, and here we have a carbon-carbon double bond. Now we are having RMgX. This is Grignard reagent, and in Grignard reagent we have a direct bond of magnesium with alkyl group. So whenever alkyl group is directly bonded with a metal, so the metal is positively charged, the R group is always negatively charged, right? So full negative charge on R group makes this a hard center. Larger size, harder center. So since R is hard, it will prefer to attack the hard center. Here, the resultant formation of this 1,2 addition. Why we are saying 1,2 addition? Because in alpha beta unsaturated system, we assign one number to oxygen, two number to carbonyl carbon, then third to the double bond, and fourth to the terminal double bond here. So this is 1, 2, 3, 4 numbering. And since the addition is occurring on oxygen, which is given number 1, and R on the carbon number 2, so that's why this addition is known as 1,2 addition or the direct addition. So in case if we have hard nucleophiles will always result in 1,2 addition, right? But in case if we have a lithium organocuprates, right? Or in case if we are using thiol, again, the sulfur compounds, sulfur is large, and organocuprates are also softer nucleophiles, right? So if we have simple lithium, it will be hard, but if we are forming organocuprate, lithium organocuprates, then in that case, it will be a softer nucleophile. So since the nucleophile is soft, it will prefer this position, right? So again, this is 1, 2, 3, and 4. So the addition will be occurring on this fourth carbon. So here you can see that R is attaching on here because R is comparatively soft because of the copper, while the lithium, which is a hard acid, will go on the hard center. Here you can see the oxygen is having negative charge, right? So oxygen is hard, so that's why lithium is binding to the hard center. Here we are having a hard-hard combination. Later on, addition of water will result in attachment of hydrogen here. So ultimately, we have attached hydrogen on oxygen 1 and the R on the carbon number 4. Therefore, this addition is known as 1,4 addition or the Michael addition. So whenever we have a soft nucleophile, then we always get Michael addition or the 1,4 addition on the alpha beta unsaturated system. So just by seeing whether the nucleophile is hard or soft, we can predict whether 1,2 or 1,4 addition will be carried out on alpha beta unsaturated carbonyl compounds. So that's all for this lecture. I hope this concept will be clear to you all. Thank you.